Hi, we're back with Nuclear Chemistry Part 2, and we're going to continue the story. Okay, so we're going to take a look. How were the radioisotopes that were found by Marie Curie and her husband? How were they found? And how is nuclear chemistry like a grape? So let's take a look.
It's a question of dissolving.
My husband is looking at me disapprovingly again.
I'm doing nothing of the sort.
You think I'm asking stupid questions to your eminent friends?
Your questions aren't stupid, really.
My mother told me never marry a brilliant man. You'll disappoint them and they'll disappoint you.
And why will I disappoint you?
By failing to avoid making her feel inadequate, I would suspect.
This woman can stay.
No, are clear you're asking questions.
So you take the ore and you dissolve into it.
Well, we take the pitch blend, which is a special ore that comes all the way from a mine in Bohemia. And then we use a scientific process to remove the elements we know we can remove and look at what's left.
And what scientific processes might you use?
These are very good questions. We crush it, which is extremely hard work. Then we boil it, which results in the removal of substance. We add acidic and alkaline solutions to it until only that which is pure remains. And there's a lot of substance to remove.
And it will be worth it.
It's very exciting.
And why are you looking at uranium in the first place?
Becquerel.
A more than competent scientist.
Becquerel discovered accidentally that uranium salts wrapped in a black cloth, left in a drawer, left an impression on a photographic plate. And he thought that the uranium was having an unusual chemical reaction with something in the atmosphere. I say it's the element itself.
A very radical thought.
I still don't understand.
Imagine a grape. How do you turn a grape into wine?
Well, you crush it and ferment it.
Yes, so imagine a grape crushes itself, ferments itself, changes its very being. And what if I told you that as the grape turns itself into wine, it releases a powerful surge of energy, power that can make things happen? You'd be excited, am I right?
I think so, yes, I would.
So science is changing. And the very people who are running science are the people who believe the world is flat. And I'm going to prove them wrong, just as Newton did. We are.
Thank you. It's a question of dissolving.
Okay. So, radioactivity. What is it used for? So, carbon-14, you probably have heard of that, of carbon dating. It's used for dating the age of things that were once alive, like fossils or things, that are dead now. Okay. Uranium-238 is for dating rocks and geological things that were not alive. Chemical tracers. So you can follow the path of a material that's radioactive in the environment or in the human body. And used to kill pests. It can radiate them. Makes our food last a little longer. Okay. It's used in medicine, but it has to have a short half-life so that it can be quickly eliminated from the body. Iodine-131 is used for thyroid cancer, and technetium-99 for brain tumors, cobalt-60 for other types of cancer. Okay, so nuclear equations. Let's take a look at how we can balance these. Charge, energy, and mass all must be conserved. That means, again, that the reactant side has to equal the product side. Okay, so instead of looking at amounts or grams of elements, we're going to actually look at the elements themselves. So 27 and 4 adds up to the 31. 13 and 2 add up to 25. This side must add up to those same numbers. So let's take a look. Again, it has to conserve mass, charge, and energy. So we start with our knowns over here again. The 27 and 4 add up to 31 for mass, and for the atomic number, the 13 and 2 add up to 25. We can use this to find the missing piece. 1 plus what makes 31? 30. And 0 plus what makes that 25? 25. And then to find the element's name, again, that is related to the protons. So you look up atomic number 25 and it is manganese. So that's how we can find the missing piece. Also, let's take a look, see if you can still identify nuclear reactions. Is this natural or artificial transmutation? Hopefully you said artificial because it's an element plus a particle. This is an alpha particle. And again, artificial does require that extra particle to get things started. Okay. Try figuring out what the X is. Remember, things have to add up. This hydrogen here is a 1. It got cut off. Let's take a look. Oh, again, let's use our knowns. 2 and 2 make the 4. 1 and 1 make 2. So on this side, all you have is energy in this singular particle. This particle must have a mass of 4 and 2 atomic number. So that makes it helium, or an alpha particle if you like. Also, hopefully you can look at this. Is this fission or fusion? Is this fission or fusion? Hopefully we're saying fission since these are being combined, fusion, since they're being combined and fusing together to make one element. Fusion. Try these on your own. Take a minute, get some scrap paper out. Okay, let's go over it. Let's take a look at how we got these. First of all, this is natural transmutation, a single element naturally breaking down. Notice the 4 and the 235 add up to 239, and the 2 and the 92 add up to 94. Atomic number 92 is uranium. Now let's take a look at this one. This is artificial transmutation. An element and a particle is needed to get the change to happen. Again, notice 22 and 0 make 22. 11 and negative 1 make 10. So in this case, you needed a beta particle to get this started. Because how can you make 10? 11 minus 1 makes the 10. Okay, so dangers of radioactivity and radioactive waste. Well, it can damage tissue. In fact, Marie Curie and her husband both did die of cancer and diseases related to the radioactivity they were exposed to. It can mutate your genes so you can pass that along to your children. So you have to be very careful. Stays radioactive for thousands of years, depending on the isotope. And if it's buried in containers, it could leak. So nuclear power plants, when they're done with their waste, they do bury them, but the possibility of it leaking or an earthquake happening thousands of years later and exposing that radiation is a concern. Again, radioisotopes are found on table N. These are not all of them, but these are some common ones. Their half-life is listed. Their decay mode, what kind of particle they emit when they decay. And when they decay, this is how long it takes for half the sample, right, to decay. So we're going to take a look at this half-life. Okay. So let's take a look at iodine 131. It's used to treat thyroid cancer or thyroid disease. Okay. All of these are natural decay, natural transmutation. The decay mode for iodine 131, go look it up. Here it is. And it's beta. This is a beta decay. So the balanced nuclear equation, well, we start with iodine 131. I can look up on the periodic table to find the atomic number is 53. The mass is given as 131. We don't use that average mass on the periodic table because we're given a specific isotope to study. We know that a beta particle will be created since it's beta decay. Now we have to figure out the missing piece. So -1 plus what will make 53? 0 plus what will make 131? Okay. So again, -1 and 54 will equal that 53. Remember, everything has to be conserved. When I look up 54 on the periodic table, it is xenon. Okay, so that's how you can use table N to write balanced equations. We're going to take a look at the half-life now. Again, radioactive substances decay at a rate that's not dependent on temperature or pressure or concentration. It's sort of its own thing. It's the time it takes for half the atoms in a given sample to decay. And you can see examples of this on table N. Let's look at an example. Let's say we have 40 grams of a sample of radium-226. How much is left after 8,100 years? Well, at the beginning, you have the full sample, right? 100% of the sample, 40 grams, right? The clock hasn't started ticking yet. It has a half-life of 1,620 years. So in 1,620 years, half or 50% of the sample will remain. Half of 40 is 20. And we have to keep going for 8,100 years. So half of the 50% will be 25%. Half of the 20 grams will be the 10 grams. Let's say another half-life or 1,620 years goes by. 5 grams will be left. Another half-life goes by. 2.5 grams will be left. And at the very end, 1.25 grams will be left. Okay, it took 5 half-lives, 5 sets of 1,620 years to go from 40 grams to 1.25 grams. Let's take a look at another example. Creating tables like this is a good way of getting the correct answer. So iodine 131, again used for the thyroid cancer treatments, starts off, had an original mass of 16 grams. How much will remain after 24 days? Its half-life is 8 days. So let's take a look here at the graph. We started here, our chart, with 16 grams at the very beginning, 0 days. The half-life is 8 days. After 8 days, you have half left, 8. Another 8 days for a total of 16 days. Half of 8 is 4. And another 8 days, 3 sets of 8 days, 24 days have gone by, and you're left with 2 grams. So again, notice you're cutting in half, cutting in half, cutting in half. Okay, try a problem. What is the original amount of a sample after 36.8 years if 2 grams are left? Well, if you look up hydrogen-3, you can find that the half-life is 12.26 years. So to find out how many half-lives have gone by, I can take the total time, divide it by the half-life, and I get the 3 half-lives will go by. And then you can work backwards in this case, because they're saying 2 grams are left. So after, you have to go backwards basically. 2 grams, go back a half-life, 4 grams, back a half-life, 8 grams, back a half-life to the original 16 grams. So again, this was working backwards. You know how much was left, and you had to figure out how much you were starting with. Okay, so those are sorts of problems you're going to see for half-life. Again, divide in half, or if you're going backwards in time, multiply by 2. Okay, good luck.